Physics is an experimental science, which means every law it discovers must in the end be measured. But a measurement is only as good as the instrument that takes it and the care with which it is used. This unit is the practical craft of measuring well, which tool to reach for, how precise it really is, and how to read it without fooling yourself. This unit builds in four moves: the instruments themselves and what each measures, the precision and resolution that tell you how fine a reading is, the oscilloscope for seeing signals that change in time, and the judgment of choosing the right tool for the job. Let's start with the toolkit. Each quantity has its natural tool. Length, a ruler for centimeters, calipers for millimeters, a micrometer for hundredths of a millimeter. Mass, a balance. Time, a stopwatch or for fast events like gates. And in circuits, an ammeter measures current in series, while a voltmeter measures voltage across a component in parallel. Two reading tricks recur. A vernier scale on calipers lets you read an extra decimal place by spotting which lines align. A micrometer uses a fine screw thread to magnify tiny movements onto a rotating barrel. Both turn a movement too small to see directly into a number you can read off cleanly. Watch out, though, for a zero error. Always check the instrument reads zero when it should. Resolution is the smallest change an instrument can detect, its finest step. A ruler resolves to a millimeter, a micrometer to a hundredth of a millimeter. A higher resolution instrument can split the world more finely. But resolution is not the same as accuracy. A finely divided ruler that has stretched with age reads to a millimeter, yet is simply wrong. A smart technique improves precision for free. Measure many at once. To find the thickness of one sheet of paper, you would never measure one far too thin. Instead, measure a stack of 500 sheets and divide. The same trick times 20 swings of a pendulum, then divides, shrinking the effect of your reaction time error 20-fold. Some quantities change too fast to follow with a meter, so we use a cathode ray oscilloscope, which draws a voltage as a moving trace on a screen. The vertical axis shows voltage, set by the volts per division dial. The horizontal axis shows time, set by the time-based dial. It is, in effect, a graph of voltage against time, drawn live. Reading it is all about counting squares. The height of the wave, in divisions times the volts per division, gives the peak voltage. The width of one full cycle, in divisions times the time base, gives the period, and 1 over the period gives the frequency. Count the squares carefully, multiply by the dial settings, and the scope tells you amplitude and frequency at a glance. The final skill is judgment. Match the instrument to the measurement. Measuring the diameter of a wire with a meter ruler is hopeless, far too costly. You reach for a micrometer. Timing a sprinter to the nearest hour is absurd in the other direction. The rule is to pick a tool whose resolution is fine enough to matter, but no finer than the task needs. And always think about how the measuring itself disturbs the experiment. A voltmeter draws a little current. A cold thermometer cools the very thing it measures. Good technique minimizes this interference and repeats readings to expose random error. Measure with the right tool, read it honestly, and your data can be trusted. Here is the whole unit as one poster. Each quantity has its tool: rulers, calipers, and micrometers for length, balances for mass, timers and light gates for time, ammeters in series and voltmeters in parallel for circuits. And resolution, the smallest step an instrument can detect, is not the same as accuracy. Boost precision by measuring many and dividing. The oscilloscope draws voltage against time. Read peak voltage from the height times the volts per division, and the period from one cycle's width times the time base. And always choose a tool whose resolution fits the task, no coarser and no finer than needed. And the boundary fence, so you do not over-revise. The full statistical treatment of uncertainties and error propagation is covered in the physical quantities unit and practical work. The detailed electronics inside these instruments is beyond the syllabus. Here it is the practical craft: the instruments, precision, the oscilloscope, and choosing well.